So let's start with session 3. We have already studied about conservation of mechanical energy. We have started conservation of mechanical energy in session 2. Now in this session, let's continue the conservation of mechanical energy. Let there be WC be the work done by the conservative internal forces on the system. Let WNC be the work done by the non-conservative forces, internal forces on the system. Let WEXT be the work done by the external forces on the system. Let me remind you that WC is conservative internal forces. WNC is non-conservative internal forces. C is for conservative internal forces. NC is for non-conservative internal forces. So WC is work done by conservative internal forces and WNC is work done by non-conservative internal forces. And WEXT is equals to work done by the external forces on the system. WEXT, we have assumed three things: WC, WNC and WEXT. Then, in accordance with the work energy theorem, all forces work is equal to the kinetic energy change. Therefore, using this statement, we can write that work done by the conservative internal forces plus work done by non-conservative internal forces plus work done by external forces on the system. Thus, sum of these all work done would be equal to Kf minus Ki. That is kinetic energy final minus kinetic energy initial, where we already know that work done by conservative forces can be written as minus of UF minus UI. How we know that? Let me refer to previous slides. Here, in the point 1, we have already mentioned potential energy, that is U, is described based on the conservative internal forces. The same thing is here. Conservative internal forces. WC is work done by conservative internal forces. Therefore, work done by conservative internal forces can be written as minus of UF minus UI, where UF stands for final potential energy and UI stands for initial potential energy. Thereby, we can write this equation as work done by non-conservative internal forces plus work done by external forces is equals to Kf plus Uf minus Ki plus Ui. How we have simplified this equation? The LHS of WNC and WEXT stands there, whereas WC, that is work done by conservative internal forces, has been replaced by UF minus UI, and thereby we have shifted WC on the right hand side to write it as Kf plus UF minus Ki plus Ui, where Kf is final kinetic energy, UF is final potential energy minus initial kinetic energy Ki plus initial potential energy, that is Ui. Considering this Kf plus Uf as the final energy of the mechanical system, we can write this as Ef. Also, considering Ki and Ui as the total mechanical energy at the initial stage of the system, we can write this as Ei. So, Ef is equals to Kf plus Uf, Ei is equals to Ki plus Ui. Therefore, the net energy would be equals to Ef minus Ei is equals to WNC plus WEXT. Further, we can study that if external forces do the work and internal forces are conservative, the work done by the non-conservative forces is equals to 0. This statement concludes to 2 points. The first thing, if the external forces do the work and internal forces are conservative, then work done by non-conservative forces is equals to 0. So work done by non-conservative forces would be 0. The second thing it would communicate is the WEXT then is equals to EF minus EI. That is, work done by external forces would be is equals to EF minus EI. Energy at the final stage of the system minus energy at the initial state of the system. Next, we are going to study about the conservation of momentum. The conservation of momentum. So let's find out what is momentum. Linear momentum of an object is given by momentum is equals to mass into velocity, where momentum is denoted by capital P, mass is denoted by small m, and velocity is denoted by small v. Thus, P is equals to m into v, where P is momentum, m is mass, and v is velocity. In case there are n objects, the total momentum would be the sum of momentum of all the individual objects. That is, in this case, the total momentum can be mathematically written as Pn, where n stands for n number of objects. So Pn would be equals to summation of Mn into Vn, where Mn would stand for mass of n number of objects and Vn would stand for velocity of n number of objects. Therefore, this equation can be written as Pn is equals to summation of Mn into Vn. It is to be noted that an object moving with a constant velocity will have uniform linear momentum unless and until an external force acts on it. This states that if an object is moving with a constant velocity, since I have already told you in the previous sessions that P is equals momentum is mass into velocity. We have already studied today as well. So P is equals to mass into velocity. Mass is never going to change itself. So if the velocity is constant, the momentum will also be constant. And thereby, until and unless an external force is acted on it, momentum will remain constant. According to Newton's third law of motion, every action has equal and opposite reaction. We have studied this law previously, that every action has equal and opposite reaction. We have also considered the example of rocket propulsion. Thus, we can also consider a different example in this case. For example, during a leap, the force applied by your legs is equal to opposite to the force applied by the ground. Like, if a person is moving on the ground, if he is walking, then the force applied by his legs on the ground will always be equal and opposite to the force applied by the ground on his legs. This states the Newton's third law of motion. To understand the conservation of momentum, let us consider a case. Let u1 and u2 be the initial velocities of mass m1 and m2, and v1 and v2 be their final velocities respectively. Thus, change in momentum of object A would be equal to m1 into v1 minus u1, since the momentum is written by mass into velocity. Here v1 is the final velocity of the object 1, whereas u1 is the initial velocity of object 1. So change in velocity would be v1 minus u1, and mass of object 1 is, that is object A, is m1. Thus, net change in momentum of object A can be written as m1 into v1 minus u1. Similarly, change in momentum of object B can be written as m2 into v2 minus u2. The same theory will apply here. m2 is the mass of object B, v2 is the final velocity of object B, u2 is the initial velocity of object B. Therefore, change in velocity would be v2 minus u2. Therefore, change in momentum would be m2 into v2 minus u2. As per the Newton's third law of motion, it can be written as FBA is equals to minus of FAB. That is, mathematically, Newton's third law is written as the force applied by the object B on object A is equals to negative of force applied by object A on object B, where FBA can be written as m2 into a2. We have read this previously also. Force is equals to mass into acceleration. And since here FBA is the force that has been applied by object B, therefore formula can be written as m2 into a2. Also we know that a2 is the acceleration of the object B, and acceleration is defined as change in velocity per unit time. Therefore, acceleration can be more elaborately written as v2 minus u2 divided by time. That is final velocity of object B minus initial velocity of object B with respect to time. Therefore, FBA can be written as m2 into v2 minus u2 divided by time. Let's state this equation as equation 2, and FBA is equals to minus of FAB. Let's state this equation as equation 1. Here A2 is acceleration of m2. That is, as I told earlier, A2 means acceleration of object B and mass of object B is m2. We have discussed this earlier. In the similar manner, FAB can be written as m1 into a1, where m1 is the mass of object A and a1 is the acceleration of object A. FAB is force exerted by object A on object B. We have also discussed previously, acceleration is change in velocity per unit time. Therefore, for object A, the change in velocity, that is a1, that is thus for object A, acceleration can be written as change in velocity, that is v1 minus u1 divided by t. Let's state this equation as equation 3. Here also we have discussed a1 is the acceleration of object A with mass m1. Coming to the next slide, we are putting equation 2 and equation 3 in equation 1. So let's revise what was equation 2 and equation 3 first. Equation 2 was force exerted by object B on object A is equals to m2 into v2 minus u2 divided by time. That is m2 into u2 v2 minus u2 divided by time. Similarly, equation 3 was FAB, force exerted by object A onto object B, is equals to m1 into v1 minus u1 divided by time. Thus, by putting equation 2 and equation 3 in equation 1, the equation 1 is FBA is equals to negative of FAB. We can write as m2 into v2 minus u2 divided by time is equals to minus of m1 into v1 minus u1 divided by time. Hope you have understood. This is FBA. This is FAB. And negative of FAB to be true. Therefore, by simplifying this equation, we can get the following results. m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. This is the mathematical equation for conservation of momentum. Here, m1 and u1 plus m2 u2 is the total momentum of objects A and B before collision. Since u denotes the position at the initial point, therefore, this is for the objects A and B before colliding. This is the state of momentum of the objects A and B before colliding. Similarly, m1 v1 plus m2 v2 is the total momentum of object A and B after collision. As we know, v is the final state of final velocity of the objects A and B. Therefore, m1 v1 and m2 v2 denote total momentum of object A and B after collision. Thus, from this last point, we need to understand that what is collision and how it happens. Collision. For understanding collision, let us try to understand the following example. Consider two blocks of mass m1 and m2. This is mass first block of mass m1. This is second block of mass m2. Both the blocks are moving with a velocity of v1 and v2 respectively. This first block is moving with a velocity of v1. This second block is moving with a velocity of v2. It is also shown that the second block is attached with a spring. Thus, few conditions. Case 1, where time is t1. This pictorial representation of collision represents that both the blocks are moving in the same direction. First block is of mass m1 is moving with a velocity v1, whereas second object of mass m2 is moving with a velocity of v2. Here the comparison of velocities is also given. That is, the velocity of object 1 is greater than the velocity of object 2. This has been very clearly mentioned here. In the second case, when time is t1 plus del t1, that is, due to the higher velocity of object 1, this object at time t1 plus del t1 collides with the second object. Thus, such will be the representation of the system, that the object 1 is colliding with the object 2. This would cause the spring to compress and transfer of velocity. Thus, thereby we can see here v1 is lesser than v2, whereas in previous case v1 was greater than v2. That is, velocity of first object was greater than velocity of second object. That only tend this object to get collide with second object. And when the collision happened, the velocity of first object get reduced and thereby it is now smaller than the velocity of the second object. This arrow denotes the same. The velocity of second object is greater now with the velocity of first object. This is our case 2. Further, going to case 3, at time t1 plus del t1 plus del t2, what would happen is that spring will exert a force back to the object 1. Like we have seen in the case 2, that the spring was exerting a force, but that force was kx in the positive direction and minus kx in the negative direction. So this minus kx force would exert a force such that the velocity v1 would get decreased, and this plus kx would exert a force on second object, that this velocity v2 would increase. This must have happened in case 2. But what happened in case 3? This, when the velocity of first object decreased, then the mass has been detached from the spring, and now the second object is moving with a pace of velocity 2, and the velocity 1, which is much lower than the velocity 2, causes the first object to get it detached from the spring and stay apart from the object 2. Here the same things are mentioned. u1 and u2 be the initial velocities of mass m1 and m2. Let v1 and v2 be the final velocities. Considering potential elastic energy of spring is half kx square. Thus, due to the absence of external force, the momentum of two blocks of the system stays constant throughout the process, since, as we see, that there was no external force applied by anyone or any other object, thereby the momentum of the blocks in the system stays constant, and due to the lack of friction, the sum of elastic potential energy and kinetic energy remains constant. These are the points which we have seen in this pictorial view very clearly. Further, we can say that total energy of the system at time t1, the spring is at its natural length, is half m1 u1 square plus half m2 u2 square is equals to E. Let's give this equation name as equation 1. Further, total energy of the system at time t1 plus del t1, that is case 2. At case 2, the total energy of the system would be half m1 plus m2 v square plus half kx square is equals to E. In such a state, the spring would be at its compression state, and the compression, we would believe that the compression is maximum. Also, we would say let u1 is equals to u2 is equals to v. Thereby, we have replaced u1 and u2 with the v. Thus, we can write that half m1 plus m2 v square plus half kx square is equals to E, where half kx square is the force exerted by the spring. Going into the case 3, total energy of system at time is equals to t1 plus del t1 plus del t2. The compression of the spring is maximum. Half m1 v1 square plus half m2 v2 square is equals to 3. Let's name this equation as equation 2. On comparing equation 1 and 2, we get half m1 u1 square plus half m2 u2 square is equals to half m1 v1 square plus half m2 v2 square. As we have already seen, let us revise. The equation 1 was half m1 u1 square plus half m2 u2 square is equals to E, where m1 is the mass of object 1, u1 is the initial velocity of object 1. Similarly, m2 is the mass of object 2 and u2 is the initial velocity of object 2. And this whole thing is equals to E. That was the total energy of the system at time t1. Similarly, total energy of the system at time t1 plus del t1 plus del t2 was equals to half m1 v1 square plus half m2 v2 square is equals to E. In both the cases, the total energy remains constant. Thereby, we have compared equation 1 and equation 2 in next slide here. So, we can say that it is not possible for kinetic energy to remain constant throughout the entire time interval, though the kinetic energy before and after collision is same. As we have seen that in previous slide, there is some change in kinetic energy happening in between in this time interval t1 plus del t1. But we have observed that there was no effect on initial and final state of the system. Thereby, it is written then, it is not possible for kinetic energy to remain constant throughout the entire time interval. Means kinetic energy may not be same, may not be constant throughout the time interval, though the kinetic energy before and after collision is same. Although the kinetic energy before the collision and after the collision would definitely be same. Now we are trying to use this exercise for better understanding of the concepts. So the question 1 says that a bullet of mass 8 grams is fired from a pistol of mass 2 kg. The recoil velocity of pistol observed to be 1.2 meter per second. Find the bullet's velocity. So we have given with the following conditions, that we have given the mass of the bullet, which is 8 grams, and the bullet is fired from a pistol of mass 2 kg. So the mass of the pistol is 2 kg. The recoil velocity of pistol observed to be 1.2 meter per second. Thereby, when this bullet of 8 grams is fired with the pistol of mass 2 kg, then the shooter receives a recoil velocity from the pistol of 1.2 meter per second. Here we are writing the given conditions of the question. Mass of the bullet, let us consider it as m1, that is 8 grams. Since we are using SI units during the numericals, thereby we need to convert 8 grams into kgs. The conversion factor we generally use for kgs to grams is 1000 grams is equals to 1 kg. So we can make out that if 1000 grams is equals to 1 kg, then 8 grams would be equals to, that would come to 0.008 kg. Similarly, mass of pistol, we are representing it by m2, and that is provided in the question as 2 kg. Velocity of bullet. We need to find the velocity of the bullet. Here it is written. That is the actual question. What's the bullet velocity? We are considering this bullet velocity as v1 and we need to find it out. Further, the recoil velocity of pistol v2. Therefore, the recoil velocity of the pistol is 1.2 meter per second. This is given in the question. Thus, going ahead with the solution, by using law of conservation of momentum, we already know the formula of conservation of momentum is m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. Since the bullet and the pistol was at rest, thereby u1 and u2 is equals to 0. Let me explain that. When the bullet was not fired with the pistol, then the both bullet and pistol was at rest. Therefore, the initial velocity of the bullet must be 0, that is u1. Also, the initial velocity of the pistol must be also 0, that is u2. Thus it is written as, since the bullet and the pistol was at rest, u1 and u2 would be equals to 0. Thus we can say that LHS would be 0 in this equation, because when u1 and u2 will be multiplied by masses m1 and m2, they will result in 0. m1 multiplied by 0 would be 0, m2 multiplied by 0 would be 0. So 0 plus 0, that would be again 0. So this whole LHS can be written as 0. On the RHS side, let us put the values, where m1 we have already known from the previous slide that m1 is equals to 0.008 kilograms. Also m2 is equals to 2 kg and v2 is equals to 1.2 meter per second. So m1 is 0.008 kilograms into v1 plus m2 is 2 kgs and v2 we have seen it is 1.2 meter per second. Thereby, by solving this equation, we would get the velocity of bullet is equals to 300 meter per second. And so is the answer of our question. What was our question was? To find the bullet's velocity. We have denoted the velocity of bullet by v1. And here we can see v1 is equals to 300 meter per second. We are going to cover the summary that we have learned today. So we have first initially started with what is energy. Energy is the capacity to do work. Further, we get to know that energy of a moving object is defined as Ke is equals to half mv square, where Ke is kinetic energy. Further, we have learned kinetic energy of a system of objects is kinetic energy is equals to summation of half mv square, where number of objects is I. That means if there are I number of objects in the system, then the kinetic energy of the total system can be written as kinetic energy is equals to summation of half mv square of all the I objects. We have also learned that when there is a tangential component in the resultant force, the speed changes and the kinetic energy changes. We have learned this in circular motion, that when there is a tangential component in the resultant force, the speed changes and the kinetic energy changes. Also, we have studied that when the resultant force is perpendicular, the speed will not change and the kinetic energy will not change. Therefore, if the resultant force is perpendicular to the velocity, then it would not be responsible for change in velocity, and so the kinetic energy will not change. We have seen kinetic energy is half mv square. So if v doesn't change, the kinetic energy would be constant, because mass is not going to change itself by any manner. Next, we can see that the work done can be written as the force acting on the object during its displacement dr. We have considered the force is Ft. Generally, we have considered the tangential force in the slides, and dr is the displacement. So work done is equals to Ft into dr, where work done can be written as dk. So change in kinetic energy is work done. K2 minus K1, we have referred to dk as earlier. The SI unit of work is joule, and it is represented by capital J. Also, the unit of work done can be Newton meter, since the unit of force is Newton and the unit of displacement is meter. So the derived unit of force of work done can be written as Newton meter. We have also fortunate to learn about work energy theorem. So work energy theorem represents as work done on an object by the resultant force and the change in its kinetic energy are equal. I have represented same here. The change in kinetic energy dk is equals to the work done, where dk can be written as k2 minus k1 or kf minus ki, where kf is final kinetic energy, ki is initial kinetic energy. So the change in kinetic energy would be kf minus ki, that would be equal to work done. This has been stated by work energy theorem. Further, work done on different objects of the system by the internal forces may not be zero. In next slide, we'll see What is power? The power is rate of doing work is power. So work done per unit time can be said as power. Therefore, mathematically, it can be written as P is equals to dW by dt, where P denotes the power, dW is the work done in the unit time or in the mean time. Therefore, we have also concluded by deriving from this equation that power is equals to F into V, where F is the force and V is the velocity of the object. This has been derived from this equation only, that power is equals to work done per unit time. The SI unit of power is watt, although there is also a generalized unit that has been used for the power is horsepower. And we have studied that 1 horsepower is equals to 746 watts. We have also got to know about the potential energy. Potential energy is stored in any object or system by virtue of its position or arrangement of parts. This definition we have studied earlier. The kinetic energy of an object remains same before and after collision. Also, we got to know that in mathematical terms, conservation of mechanical energy can be expressed as work external is equals to EF minus EI. That is, if the work done by the external forces on a system, if there is some work done by the external forces on the system, then the conservation of mechanical energy can be denoted by EF minus EI, where EF is final energy of the system and EI is initial energy of the system. After learning the conservation of mechanical energy, we got an opportunity to learn conservation of momentum, where conservation of momentum can be mathematically expressed as m1u1 plus m2u2 is equals to m1v1 plus m2v2. Here, this mathematical equation states that the momentum before collision is equals to momentum after collision. Thus, u1 and u2 are the initial velocities of object 1 and 2, whereas v1 and v2 are the final velocities of object 1 and 2. Similarly, we can see m1 and m2 in our both LHS and RHS. m1 is mass of object and m2 is mass of object 2. Thus, conservation of momentum equation mathematically expressed as m1u1 plus m2u2 is equals to m1v1 plus m2v2. Here we close our session and close our class of week